looking at just cities in North Carolina. But before doing that, I would like to talk about the different types of geocode data that is available in MATLOG. So I'm opening up the MATLOG documentation window. And if you scroll down, there's actually an entire section on geocoding functions. The ones that we'll be using for this video are primarily the longitude, latitude to city and the make map functions. We'll also talk about the Mercator projection function and the inverse Mercator projection function. The actual data that we'll be using for geocoding is at the very bottom of this documentation window. And if you look, there's the North Carolina city data. And then there's also data for the entire US cities. And it's also data restricted for cities of 10,000 and 50,000, smaller data sets that are subsets of the larger US city data. There's also county data, zip code data, and US Census block data. That's essentially all the demand point data that we'll be using. There's other data for US roads, the road link and road node data, two separate data files. Those are the primary sets of geocoding data that we'll actually be using throughout the semester. In terms of other countries, in MATLOG itself, there's no data for other countries, but it would be possible to develop similar types of data for geocoding for applications outside the United States. So let me go ahead and close this window. We can also look at the North Carolina geocode data directly. And here you'll see, and this is common for all the different data sets, so this is not specific to the North Carolina data set. What it shows is basically the one option of using it is to just call NC City and assign it to a structure. In this case, we'll use lowercase s. There's also an option of looking at the data that's actually output, which in this case is three different sources of data. One is the name of the city, and then XY is an array constituting the longitude and latitude in decimal degree. And then there's a third data source, which is the population, and it's based on the 2010 census. So probably around 2021, we'll go ahead and get an update for this data to represent the 2020 census. So this is the not the most recent data. The Census Bureau actually publishes intermediate estimates of what the population is between censuses that occur every 10 years. So it's, using 2010, we're a little bit out of date relative to 2018. And there's other formats for accessing the data, and I think it's best to look at this one in the context of the examples as we go through the script. So this is just an example of the detailed format, and what you'll see is for all the different data sources, it's pretty much the same structure. So first we're going to just call the NC city data, and what I'm doing is I'm just hitting F9, which is to evaluate this selection, and what I get returned is a structure with these three different fields. Turns out there's a total of 87 different cities in North Carolina, and that's not all of the cities. If we go back to the help information, it's cities that have at least 10,000 people in them. So if we restricted it to something less than 10,000, we'd get a greater number than 84. If we went to like 50,000, we'd get a lesser number. So 84, I think I chose that just because it's a reasonable number in terms of representing most of the population of North Carolina. And then as a structure, we can actually access the individual fields of the structure. So if I do this, I get a listing. In this case, if we look at what answer is, since I haven't assigned it to anything, it's actually an 81 element cell array. And cell arrays are very convenient for storing names of cities. And the reason is that each name of a city will have different lengths. So if we wanted to store this as a character array, we would essentially have to make room in an array for whatever the longest string is, which in this case looks like Hendersonville and Elizabeth City, Southern Pines, Roanoke Rapids. All of these have the maximum string length. So we'd have basically array space that would need to be occupied for all of this wasted space. So one advantage of a cell array is that it only stores enough space for the number of actual characters needed. And as you get larger and larger strings, the advantages of using cell array as opposed to a character array become greater and greater. And a character array is treated just like any type of numeric array in MATLAB in terms of being a fully occupied array, so there's no space savings. So it's a big advantage having cell arrays when we do with things like labels for cities and other applications. In terms of cell arrays, I'm assuming you've already looked at the basic concepts in MATLAB, so this is just a further discussion of structures and in particular cell arrays initially. So I'm just going to define a cell array. In this case, the cell array has two elements, and each of these two elements are two-element arrays, essentially just two-element row vectors, and each row vector has these two elements. If we wanted to actually look at the two arrays and see what is the information inside of the array, we can use the syntax of these curly brackets with the colon. So just like we do with a regular numeric array where we use parentheses with a colon, here if you look, this is not a parenthesis. If you look a little closer, it's actually a curly bracket. So with this curly bracket, we get reported back two instances of this answer. So what happens is it first prints to the command window the first element and assigns it to answer, and then it prints the second element and assigns to answer. So if we look at what answer is, it represents just the last one reported. So we're getting multiple values reported to the command window, and that's an example of essentially what they call in MATLAB a comma separated list, where as a result of calling one command, you'll get multiple outputs. And in dealing with that, you have to be a little bit careful in terms of there's specific functions and things in MATLAB when we have this comma separated list output. So just be aware of that. It's not the normal thing you would expect when you access the elements of an array. And you'll see that in the cell array. M is a regular numeric array, 2 by 2. And this is an example we could redefine the cell array C as having now a 3-element vector as its second element. And we can access the data. If we tried to do a similar thing with a numeric array, you see we get an error saying that the dimensions of the numeric array have to be the same. That's why, like in the labeling example, we'd have to pad the shorter elements so they have the same length as the maximum element. Going back to our structure, those are the 3 different fields of the structure. One nice thing about cell arrays is really they're a general purpose container, and we can throw really anything into the container and access it, and also we can nest at any level of detail. So in this case, even though we already have 2 numeric array vectors, we can add a 3rd element and define the cell as having a 3rd element corresponding to that entire structure. And here, if I access it just with parentheses as opposed to curly brackets, I get returned a 1 by 1 or single element cell array, which corresponds to the value of the cell array. So just like with a numeric array, if we have numbers in it, the cell array is a number, an array of numbers, and all of the elements are numbers. So in the terms of a cell array, if we use the normal parentheses to access an element of a cell array, we get a cell array returned. If we want to get the actual elements inside of the cell array, then we have to use the curly bracket notation. So if I do that, I get the entire structure returned. So I think you can see how this becomes actually very convenient, especially when we're starting maybe at a low level doing some work. We can take all of our results. We can essentially take the entire workspace, take all of the variables that we've defined in a workspace, and just throw them all into a cell array and make that just one element. And then we can look at another version, a completely different problem, take all of those variables, make that a second element in a cell array, and keep doing it. And we essentially then have records of all the data we used in different versions of maybe the same problem. And then we can take all of those and just make that a single cell array element, in another larger cell array. So sort of like the idea of like what's the universe, it's turtles all the way down. Well, with a cell array, you can basically say you can put cell arrays all the way up in terms of you can keep encompassing larger and larger collections of data. The tricky thing is you have to be able to then keep track of what's in each element. So that's one of the reasons that structures are convenient in other cases, because with structures you can actually label the fields so it's a little bit clearer what you're actually looking for. A cell array, you basically just have a numerical index into the different elements of a cell array. So continuing then with our example of using the geocode data for North Carolina cities, instead of getting the entire structure and then from the structure having to extract the different elements, in this case, say all we want are the longitude, latitude, and the names, and we're really not interested in the population data from the US city. Another way of accessing it, instead of just in taking the entire set of data, which would be the call we did originally to NC City up here, we can actually specify just the individual data fields that we want as output. So in this case, I'm just going to give the names of the two data fields, X, Y, and name. And when I do that, I'm hitting F9. What gets added to my workspace now are two elements. One is the 84 by 2 array of longitude and latitude data, and then the other is a 84 element array of city name data, and we have that data immediately available. Okay. And say we have as our first task, we want to identify where in that data is the data for Raleigh. And what we can do is use the MATLAB command string compare. And what it does is it looks into the cell array of city names and then looks for the name Raleigh. So when we execute that, what we get returned, if you look over at the answer over here, what we get returned is an 84 logical array. And the only true value is this element right here. And that then corresponds to where Raleigh is in that list of 84 different cities. To be able to utilize it, I'm going to assign it to a logical vector is. Is sort of my default logical vector. That way when I'm looking at code and I see a variable with is, I know that it's intended to represent a logical vector. So that's a convention that I use. I also use index if it's an index vector. Index vectors are particularly difficult because if you look at the class, they're actually numeric values. So their role as an index vector is only something that I'm doing personally. I'm interpreting it as an index vector, but MATLAB itself doesn't know it's an index vector. There's no class information associated. In contrast, a logical vector is actually defined as a logical vector. So if you try to do something that can't be done with a logical vector to a vector, you'll get an error message. So the index one is something that I maintain internally in terms of when I use MATLAB, but it's not part of MATLAB. That's something with an object-oriented language. You could define a index vector as a special class and then be able to catch errors where you're doing something with the index that's not correct, and it would generate an error message. The problem with that is it would add extra overhead, especially in MATLAB, of being able to use objects. There's a little bit of extra object overhead in MATLAB. So one of the reasons that I haven't defined it as an object is to keep the speed of execution fast. I guess as computers get faster, maybe it will become less of an issue. And MATLAB itself has gotten a lot faster in terms of being able to implement different object-oriented capabilities. So that's something that could be added in the future to make using index vectors more robust. It's a source of a lot of errors as you do coding in MATLAB. There's a function in MATLAB that tells you the number of non-zero elements in a logical vector. And if I do that, I get 1 as expected. I can also define, and there's a function called find, and it looks into a logical vector and then returns the indices corresponding to the non-zero or true values of the logical vector. So this is essentially the way to create an index vector. So here I get the index 66, which corresponds to Raleigh. Then I can use that index in the cell array name and I get Raleigh returned. I can also access the longitude and latitude. Notice that this is negative, and that's because the longitude is in the western hemisphere, so that's all negative as opposed to eastern hemisphere. And then the latitude is positive because Raleigh is in the northern hemisphere as opposed to southern hemisphere. If I wanted to just get the XY directly as opposed to doing both of them, I could just call XY by itself. And then I get the same XY array of 84 elements or 84 rows of longitude latitude. Another way of using NC City is to give the data that you're interested in and then just the index of the data that you want returned. This is especially useful when you have very large data sets of, hundreds of thousands of data elements. It's not convenient. It doesn't really, it's not nice to have returned to the command window a million elements. It kind of fills up your entire screen with data. And, so it's nice to be able to just access a subset of that data. So one way of using the geocode data in MATLAB is just to give the index vector. And when I do that, I can immediately just get the longitude, latitude of Raleigh, and I essentially ignore all of this other data. And another use of it is I can actually take all of the data and get all of the fields of data just for Raleigh. So I get the name, the longitude, latitude, and then I also get the population, which in 2010 was 403,000. Now it's probably closer to maybe 500,000. I'm not sure what the current population of Raleigh is. Okay. The next thing is in terms of being able to, given a name of a city, be able to actually then automatically determine the longitude, latitude. What we'd like to do is be able to access the data and basically just give it the name of the city and have it return the corresponding element from this array of longitude, latitude. And the way to do that in a convenient manner, we'll be using some of the string compare features, and we'll also be using a function handle to help hide a lot of the messy details of using the string compare function. So using multiple commands, the first example is we're using string compare, and we're going to then compare Raleigh to the names returned from the structure of all the North Carolina cities, and then we're going to call the find command to return the index. So again, that gives us 66. So this is just doing what we did in multiple commands here, all in one line in this command. We can then take that index, look into the XY, and get our longitude, latitude. What happens though if instead of typing Raleigh with a capital R, the way it's actually represented in the name cell array, if instead we used a lowercase r, we wouldn't get an error message, but instead we actually would get an empty result. So the result here returned is, this dimension is actually 0, and that's indicative of an empty vector. And so basically it's telling us that it was not able to find anything. The reason it didn't generate an error is that in many cases you don't want to stop your program running because you can't find something. You just want to deal with the fact that that city's not in the data and then do something else. So typically it's not something where you'd want to generate an error. So in this case, you get an empty return, and then if you do want to make it an error, then it's up to you to actually add a check to see if it's empty. Then you can raise an error flag and indicate that it is an error in terms of your context. So in terms of the data structure, if we try to then pass that empty result, we get an empty result returned from the XY. Again, essentially no information because there's no city corresponding to a lowercase r. We can then if we want to take this result of using the string compare function and hide a lot of the details, we can use a function handle. So what I've done here is I've created a function handle called city, which is in this case is the North Carolina city name, and it returns the longitude, latitude. Actually, it's not just North Carolina, it's any structure that has the name of a city and longitude, latitude in it. So this would work for other data structures, not just North Carolina. So when I do this, I get this data structure, and essentially it's just doing the call to the string compare to get the corresponding index. In this case, string compare returns a logical. So in addition to an index vector, we can also use a logical vector to access elements within the XY. And now I can then use this function handle, and I get my longitude, latitude back for Raleigh. I can also, what if instead of using the North Carolina data, I wanted to use the larger US city data? Well, if I do that, I'm going to, again, I'm F9ing to actually execute each selection. In this case, instead of getting 84 values, I'm getting almost 30,000 elements. And that corresponds to all of the US cities. And these are down to the smallest cities, under 10,000. So this is a large data set. If I then wanted to use it to get Raleigh from that larger data set, I actually, instead of getting a single result, I'm actually getting 5 different results. And if I look, the Raleigh data is actually the 4th element. So what these other 4 correspond to are other cities in North Carolina, outside of North Carolina, that have the name Raleigh. there can't be two cities with Raleigh in North Carolina because the state, as part of incorporation of a city, makes sure that they don't have duplicate names within a state. But between states, you can have duplicate names. I could do all of this directly instead of first having to save it to a structure. I could just give the name of the geocode data, U.S. cities, and it would automatically then incorporate and give me the same result. So I don't, I basically don't have to define a structure. I can do it all independent. And the advantage of doing it this way is you don't have to create in your workspace this temporary structure that contains all of the city data. In this case, you're basically letting the function handle do all of the work and hiding all of the intermediate data returned as part of determining this longitude latitude result. Okay. Here what I'm going to do is define it just for the North Carolina city data. So in this case, instead of having to have two input arguments, here I just have to have the name of the city. So I'm restricting it to just North Carolina. So if I do it this way, I get that single result. So that would be a convenience. If I know I'm just going to be dealing with North Carolina city data, I can define a function handle with just one input. Again, if I go to the function handle with a lowercase r, I get that empty result returned. So it turns out in MATLAB, instead of using the string compare, there's a string compare I, and what that does is it makes it insensitive to the case of any of the string values. So essentially it would match up the lowercase. So when I use that other version of the string compare function, and then if I call it with the lowercase, I get the result. So that would be convenience, because that way if it doesn't matter if the person inputs either lowercase or uppercase r, it's still going to work. And then if I wanted to add a second city, here I'm going to do Boone, North Carolina. Again, I'm taking advantage of using the case insensitive version, so I don't have to capitalize the B. I get the longitude latitude of Boone, North Carolina, which is really in the far west mountains of North Carolina. The city is actually named after Daniel Boone, and it's the home of Appalachian State University. So I can take that second city, and if I want to determine the great circle distance between Raleigh and Boone, North Carolina, since I've defined the Raleigh longitude latitude as XY Raleigh, again I'm using XY for Boone to indicate a single value of longitude latitude as opposed to capital XY when I have an array of multiple values. Again, that's just a variable naming technique that I use to keep track of what I expect the actual data to be, or at least what I intend the data to be. So I get that result here, that if I apply the distance function, here I'm using, instead of 1, 2 for rectilinear Euclidean, I'm using the two characters mi to represent miles. I could also use km for kilometers, and that would get the result in kilometers. So in terms of miles, it's 171 miles. That's sort of as the crow flies, great circle distance. The actual road distance would be greater than that. And I could do, instead of a single city, I can also look at what is the distance from Raleigh to all of the 84 cities in North Carolina. And if you look, you can see these are all the different data results. Here's a 0, so this corresponds to the Raleigh, which is right at itself, so it has a distance of 0, and that corresponds to the 66th element, which I knew from my index vector. So then now that I can do this type of thing, one of the things I can do then is to determine from Raleigh which city is furthest away from Raleigh. And what I'm going to do is first define a distance vector d. And if you look, d is a 1 by 84 vector of double representing the great circle distances. And then I could just apply the maximum function, and what I get here is the maximum distance of just under 220 miles. And in most applications, that's probably not the most useful thing, the actual mileage. What you want is, what is the index of the city that's furthest away? So essentially what we want is the argument corresponding to the maximum. So in MATLAB, one way of doing it is, instead of just doing the maximum, you can supply a second output argument, d, and then what it returns is both the distance, and then the second argument is the index corresponding to that maximum. So that's typically more of what we're really interested in, and the reason is that we can then take that and then see it's actually Asheville, North Carolina. is the city furthest away. Cities that have at least 10,000. There are cities that are further west from Asheville, but their populations are less than 10,000. There's a relatively new feature in MATLAB where if you use the caret, not the caret, but the tilde character as a first argument, then that tells MATLAB to not report that output argument, to essentially ignore it, and only report the non-tilde result, which in this case is just the single index vector. So instead of assigning it to two separate values, it just returns as a single output. The problem with that is to be able to use it, we can't use that inside of a function because we first have to return this argument to our workspace and then use that workspace variable inside of another call. So to avoid that, which is not the most convenient use, it's actually more convenient to use a function that just returns that index. And that's a function that's defined within MATLOG as argmax. There's also a argmin and an argsort. Other languages like Python in its NumPy toolbox has argmin and argmax defined as part of the language itself directly. So it's unfortunate that MATLAB doesn't, but as a result of that, MATLOG does have that capability, so we are still able to use that feature. So with that, we can get 5 returned directly. And you'll see later how that becomes a convenience, being able to use argmax directly just to get the index without having to go through an intermediate step. So given now that we can access the data and then select elements within the data, and we can also determine great circle distances, some of the things that we can then do with that, one of the first things we can do is plot the data. So here I'm going to be using that geocode function, makeMap. So if I highlight that and just F9, it creates a map. And if you look, you can see the map really corresponds to the entire world. And it has a Mercator projection. And it has the major lines. This is the equator, Tropic of Capricorn, Tropic of Cancer. And then it has the up here, I think, is the Arctic Circle. So the lines plotted here are the major lines that you'd want to see in a map of a world. And that's sort of a default. So if you do make map, you get the entire world. In our case, though, we're really just interested in North Carolina. So instead of looking at the entire world, another way of calling this is make map and then give it a set of points. And if I F9 this, what it does is it focuses in on this portion of the world containing the set of points. So what I'm doing is essentially taking all of the points, and then I'm taking a bounding box that incorporates all of the city locations, and then I'm expanding a little bit. And the reason is that I don't want the some of the points to be right on the boundary of the plot, so I put a little bit of white space beyond the bounding rectangle that contains all the points to make it look a little bit better. And then it zooms in, and here's where I can then do subsequent plotting. Notice that when I use the makeMap command, it creates a figure window, and there's another menu item that has commands specific to the MATLOG things that we'll be using. So there's MATLOG help, about MATLOG, and so on. So that information is available. Right. And then with that, one of the things we can do is if we want to plot all of these cities, we can use the same line specification characters that are used in the regular plot command. Those all carry over. If we F9, then it automatically plots. Notice that it immediately brought it to the front. So within the pplot command, it executes the SHG, bring the graphic to the front command directly. So we don't have to include that at the end of our plot command like we were doing when we were using just the regular plot command. And so this represents the names of the city, the points of the city. And then if we want to add labels representing the names of the cities, you can see here you can see that a lot of these labels look like they're overlapping. I'm going to expand this so it occupies the entire window. And here you can see it's gotten a little bit better. There's still a little bit of overlap. This is an example that I was talking about in the previous video where I'm using the Delaney triangulation to try to determine locations for the labels such that there's minimal overlap. And I can take this, and if I click here, I can say I want to zoom into the triangle area. Then at this level of detail, there's essentially no overlap. So it's only when I'm looking at a much larger portion of the state that there is some overlap in terms of labeling. So this shows the basically the center of the cities. And a question would be, what longitude latitudes reported for Raleigh and for Cary? Well, it's essentially the population centroid that is reported. Obviously, Raleigh and cities occupy quite an extensive geographic area, and the point chosen then is to take all of the population, all of the households essentially in Raleigh, and take that population and determine where is the centroid such that it's balanced. So a city that has a large unincorporated area with low population, the centroid reported would be closer to the middle of where all the population is. And for most logistics application, that's really the behavior that you do want. Here I'm going to reset to the original view. I can reduce it back to the smaller size. Okay, here and then what MATLAB is doing when it does the make map command, it's using the Mercator projection. So just an example, there's two geocoding functions in MATLAB that give you access. For most of our uses, we probably won't need to use this too often, but it's nice to be aware that this is available. So here I'm just redisplaying the longitude latitude of Raleigh. And if I wanted to determine when I actually am going to plot the longitude latitude, what is actually plotted in the plot window. So here if I do the project command, it's actually showing what's being projected. And if you notice, the longitude stays the same, minus 78, but there's a change in the latitude. It goes from 35 to actually 38. And the reason is if you look at the window here, the way it's reported, you can see that Raleigh actually it corresponds to the original 35.8 right in this area right here. But in terms of projecting it, the underlying plot is actually at value 38.4 because of the projection. So to make it actually look like it's projected correctly, there's that difference. So underlying the data is actually 38.4, but that's meant to represent a latitude of 35. So to be able to determine then what's the underlying, we can take that projected value of 38, and then an inverse projection then gives us back the original longitude latitude value. So the 38 is what's the underlying value, and then 35 is what we mean to represent. And that's a way of getting access to the data that is sometimes useful. At least initially, none of this is going to be relevant, but just when you see these two functions, that's essentially what's happening. And the nice thing about a Mercator projection is that it only affects the latitude or y variable and leaves the x unaffected. Okay. And then one of the other things we can do, now that we can do geocoding and calculate great circle distances, we can solve a location problem. And one of my favorite location problems is to determine what is the optimal location in North Carolina if you were going to locate a single facility to serve all of the cities in North Carolina. So we can take our location procedure and now do great circle distances and use our geocoded city data. So the first thing I'm going to do here is use the distance function, use the longitude latitude data. Here the function handle is going to have a point xy corresponding to the location of the city, and then I'm multiplying it times the weights, and in this case the monetary weights for this location problem are going to be the population. And here I'm taking advantage of the fact that I know that the structure returns population as a column vector, and then the distance is returned as a row vector. So here I'm actually taking the dot product. So I'm getting a single value representing the total cost. I can then use the fmin search procedure, and I get this longitude latitude as a result. If I want to see where it is in North Carolina, if I plot, you can see there's a little green line here. Let me blow this up a little bit. And if you look, you can see that the line itself is actually near Asheboro, North Carolina. If we want to see what city does that correspond to, what is the closest North Carolina city? Here I'm using the argmin function, and the advantage of doing this is that that index returned by argmin can be used directly inside of the cell array of names and give me just the string of the name. So that's the first example of what's the utility of using argmin as opposed to having to first save the index value and then use it inside. So we basically save one step doing it this way. And we look and we see that, yes, indeed, Asheboro is the closest city. And there is another function that's part of MATLAB, and it's called longlat to city. So instead of being a function handle like we did for a city to longlat, which we defined as a function handle, longlat to city is actually a built-in function within MATLAB because that requires more database lookup. So if we execute this, then what it returns is a string. It says the point XY is 24.82 miles southeast of High Point, North Carolina. And is that really the closest? Well, to get more information about this function, if we pop open the document for longlat to city, the relevant thing is what it's actually looking for is it's using the US city data of at least 50,000. So the population of the cities have to have at least 50,000. So what happened is when we call this function, the largest city with at least 50,000 in North Carolina is High Point, whereas before we saw on the map that it was actually close to Asheboro. So Asheboro then obviously has less than 50,000 population. One of the reasons that as a default longlat to city uses 50,000 is that when I'm typically looking at problems where I'm not dealing with maybe North Carolina and some other states where I'm familiar with some of the smaller cities, if I'm doing something out in Montana or Oregon, California, I probably don't know a lot of population 10,000 cities in those states. But what I do find is cities that have at least 50,000 population are likely to be locations that I'm somewhat familiar. So I'd rather know that I'm, 30 miles south of a city I'm familiar with than 2 miles from a city I've never heard before, because that doesn't really help me in terms of placing where I'm actually located. You can also use longlat instead of using the default 50,000 data set. If I wanted to use all of the US cities, then I can actually get a result saying the location is actually within the city boundaries of Franklinville, North Carolina. That just means it's within a few miles of the population centroid. And a small town like Franklinville, has even less than 10,000 population. If I do want to restrict it to just 10,000, which is the same data set as NC City, then I do get that it's 5 miles east of Asheboro, North Carolina. So again, those are just different examples. If you're familiar with North Carolina, and if you think of what thing that people from the whole entire state go to that's close to North Carolina, one thing that comes to mind, especially if you have children or something, you've probably made trips to the North Carolina Zoo. It's a large, very large zoo with animals that are in natural habitats. So, it's definitely something that's worthwhile to visit. If you look at the zoo information, if you go to the web and type into Google North Carolina Zoo and try to get the longitude latitude information, what you get returned is the decimal longitude latitude, but it actually gives it as latitude and longitude. So it returns the latitude, essentially the y value first, followed by the x value. So to be able to plot it, if we plotted it, we'd get an incorrect location. So to make sure that it's correct, we can use the flip left-right command. And what that does is it turns around and the orientation of this row vector. And then I want to plot it as a black triangle. So when I do that, it plots it, and you can see that right here is where it is, and it's actually close to the optimal location. So click here. Oops. We turn the zoom back on, and I'm going to zoom so I'm a little closer to this location. So what you can see is the population centroid of North Carolina is within probably just 5 or 6 miles of the zoo location. So I've always wondered, I've never gotten any, really further information about whether it's true or not, but it would be interesting to know that when they were deciding on what would be a good location for the North Carolina Zoo, was there any type of location analysis? In some sense, it's sort of equal distance between Raleigh and Charlotte, the two main population centers, and a little bit closer to Winston-Salem and Greensboro. But relative to all of the major population centers, it, on the face of it, it looks like a pretty good location. And then when you do the proper location analysis, it turns out to be very close to what the optimal is. So I've always wondered about whether that's just a coincidence, or was there any thought given to it, or really just anybody knowing the population of North Carolina looking at a map maybe would pick an area. Most likely it was probably that somebody donated a large parcel of farmland that was then converted to the zoo and maybe had nothing to do with it, and it's just a coincidence that it ends up being this closely located. All right, there is one last example that I'd like to point out with respect to this type of location problem that we can use. And it relates to some of the things we talked about earlier when we were using different nonlinear optimization routines. And we talked about, and we primarily used the Nelder-Mead direct search, that amoeba that uses a series of triangles. But we also talked about using gradient-based search. And now that we have MATLAB up and running, we can actually present, I think, an interesting result. And the reason is that we can use a function, and the function is called mini-sum-location, and it's developed then as part of MATLAB. So instead of using fmin search directly, we can use a MATLAB function that then inside of this function calls fmin search. Question is, why do this? Well, today it's probably not that important, but years ago when computers were slow, using the fmin search all the time would have been very time consuming for a lot of location problems. So in many cases, it was actually better to use the gradient base. You basically got results much quicker than using the Nelder-Mead. And for simple problems, the limitations of gradient-based techniques were not that relevant. Solving single facility location problems, it's essentially a convex optimization problem, and the gradient techniques work really well on it. So we didn't really need the extra capabilities of the Nelder-Mead approach. So the reason that the mini-sum location function was developed is that it allowed that technique to be used, and you could then control which type of search technique. Now I pretty much always use, if I'm using fmin search, by default it basically does both approaches, and in 99% of the time it's going to give the same result, and in some cases there's slight differences. So it essentially does both gradient and Nelder-Mead, and then it returns basically the best result from both of those. So first I'm going to create a new plot command. And here is the syntax for the mini-sum location problem. First argument is the set of existing facility locations. Second are the weights. And in this case, it's uppercase, so we can have more than one row. And we'll see later that we can use it when we're solving multiple facility location problems. P again is the indication of metric distance, or the string mi for miles. And then there's some additional arguments. V is if we have multiple new facilities that we're locating. X0 is a starting point, just like with fmin search. And then the last argument is a set of options that we can actually specify for this. So if you want to see what the options are, you can call fmin search with defaults, and it returns the default values for all the different options of using the structure. And the one that we're going to be using primarily is the search technique option. 3 means to use the best of gradient or Nelder-Mead. And then there's another option, whether or not to do majority check. What that does is it looks and sees the weights, and if one weight has more than half the total weight, instead of solving the nonlinear optimization, it just returns that value because it knows via the majority theorem that that is the optimal result. Again, nowadays it's not that big of a deal, but back when computers were slow, that would potentially really speed up some applications. What we're going to be doing is using iteration plot, and what that'll do is it'll take that map of the world, and depending on where we start, it'll put a red dot at all of the places that the mini-sum location procedure looked at and calculated the total cost. So wherever we start, it's going to put a point there, but then it'll plot all of the different places that the search routines actually look at as part of the solution process. And to do that, instead of using the default empty value for iteration plot, we're going to give it the GCA is get current access. That's something you can always execute in whatever figure you have open, and whichever one's to the front being displayed, it'll give a handle to that axis so that later on you can actually plot things in that axis. So I'm telling the function by assigning this option to the current axis that when it does iterations plot, to plot it on that map of the world that I've just created, because that's my current axes. We have other figures that I've not closed yet. If you look at it, there's several open, but the most recent one, the one that's current, is that empty map of the world. So I'm going to execute that. And here, to make it interesting, instead of starting in the middle of the cities of North Carolina, I'm going to start at longitude, latitude 0, 0, which is, if you look at the world, that's 0, 0 is this point right here. So it's just off of the Gold Coast of Africa. at equator and Greenwich mean 0 point. So that's where the optimization is going to start, and then it should be heading over to North Carolina and then ultimately settling near Asheboro as the ultimate result, because we're going to solve basically the same problem that we solved previously. So this is my starting point, xy0. I'm going to define P to be my set of longitude latitudes for all 84 cities. W is going to be my weight vector, and here I have a note that it has to be a row vector. By default, if I do S population, it's actually a column vector. So what I'm doing here is I'm squeezing it down into a column vector just in case it was something else, and then taking the transpose. So this forces it to be a row vector. It turns out the mini-sum location procedure, the fact that W is a row vector is important because that corresponds to the weights of a first new facility to be located. The fact that W is an array means that it can have multiple rows, and the multiple rows of weights then would be the weights for each new facility. So because we can do multiple things, W then has to have a context in terms of row versus column. I'm going to execute that. And then here I'm going to first start with the gradient-based search. So I'm going to set the option for search technique to be 1 instead of the default 3. And now when I call fmin search, PW miles, then here's the V. Since I'm not doing multiple, I'm just going to leave that empty. And here's my starting point at longitude, latitude 0, 0. And then here's my option structure. And what it's doing is it's actually displaying the command window, the objective function values that were looked at. And to see what's happening, if I actually look at all of this, let me zoom in a little bit so you can, I think, see a little bit better. And here are all the points. So here's where it started, this purple circle right here. And then the gradient optimization made just a short step away from there and realized that it was getting a decrease. So in terms of the surface, it was heading down in this direction. So it looked at another point over here. But after these 2 points, it was able to then at that point say, hey, I'm really making good progress, so I can take a really big step going forward. So from this point, it took a step all the way across the Atlantic Ocean to just north of Cape Cod over here near Boston. And I think there was then at this point, it actually, let me reset. It actually, I see another point up here right at the Arctic Circle. So the gradient was looking over there, but at this point it realized, hey, my cost is going up, so I'm not making progress. So the next direction was from Boston instead of the Arctic Circle, it started going in this direction. And so down from the Arctic Circle, it probably went somewhere off the coast of the Atlantic, and then it kept falling further down. And then as you zoom in, very quickly, there's not too many points, and very quickly was able to narrow down that location right near Asheboro. So in terms of total number of function evaluations, it actually did that very quickly. So I'm going to do the same thing then for Nelder Mead, so you can see the difference. But before I do that, I would like to erase all of the points. One way of doing it is you can do erase last line tag, Control D. But another way of doing it, instead of doing it with a menu, if you wanted to do it in a script, you can execute this command, delete find objects, and then as I plot those points, I label them as iterative plot, so I'm able to find those and then I'm deleting them. So when I do that, if I'd go back and look at the figure, it's eliminated all those red points. So now I can change my search technique to 2, which is just do Nelder Mead and do what I did before. Notice the difference as we do this in the number of points. These are all the points that Gradient looked at. Now we're doing Nelder Mead. You can see it's a lot more points that are being plotted. It's still running. It's still running. And finally got a result. Nowadays, the reason it took so long is I was actually plotting the results, so it slowed it down. On my computer, or really any computer today, it would really be able to give you that result in a fraction of a second, so it's not an issue. But again, 15 or 20 years ago, with the computers of that day, That would be probably a couple minutes or at least a minute or two calculation, based on the computers of 15 years ago, versus gradient based was just a couple seconds. So the difference was significant back then. Again, that explains why that was considered then versus now, where probably not as important. We can zoom in, and you can see here the Nelder-Mead, it was actually doing a lot of work here. Let me zoom into this portion. Just when it first got started, if we keep zooming in, there's a lot of calculations. So you can see these points here. These are all the little triangles that it looked at. And you can see it kind of, if you could try to visualize this, it started off with a triangle like this. It saw that this value was increasing, so it flipped over to here. And then that looked promising. This value was lower, so it expanded over to here. And then that was promising, so it expanded over to here. So you had a series of expanding and contracting triangles that then started moving in this direction. So it then was able to then move, and again, it's not moving fast. It's not making a big jump across the Atlantic like the gradient. It did it in a fairly small series of steps. And here it's basically going, and it's over in Nova Scotia somewhere. And it looks here, there's a lot of red points, so it's kind of nervous about where to go. It's tried to go this direction and saw that there was no improvement. So over time, you can see it almost goes this direction, then almost makes like a U-turn, and then starts heading in this direction. At this point, because the surface is actually fairly flat as it gets close to the optimal, you can see that the spacing between these points gets quite large. And it takes quite a while to actually narrow down to North Carolina as being where the optimal is. So there's a lot of searching going on. We can keep zooming. Keep zooming. So even as we're getting close to Asheboro, depending on what the resolution, we can basically set the tolerances. So based on the tolerances, the final results you can see that are, these are probably all just a matter of several hundred yards or probably a fraction of a mile separation between as it's narrowing in on the opposite. So imagine when you're doing it, and what the Nelder-Mead is very flexible in terms of the type of optimization. If we were using it for a problem where you can imagine like every evaluation of the function, maybe we're actually running a simulation to simulate the performance of some system. So every time we evaluate, we could be spending, even on a fast computer, several minutes of time. So running Nelder-Mead like this would probably take 20 hours of computational time. So as a result of that, you might want to pay a lot of attention to picking a starting point that's really close, or maybe using a gradient-based technique or something else. So depending on the cost of evaluating your function, it really determines whether or not Nelder-Mead is feasible. One last issue with respect to Nelder-Mead, it's also important relative to the dimensionality. In this case, these are just two-dimensional search techniques, and the difference between gradient versus Nelder-Mead, if you think it's interesting just in 2 dimensions, it becomes even worse in higher dimension. So if we had an optimization problem where if we were trying to solve something that had 40 parameters, we'd be searching in 40-dimensional space, and 41-dimensional simplices that Nelder-Mead would be looking at would be very time-consuming to evaluate, and it would take quite a lot longer than any gradient-based technique. So that's why gradient search is still used for other than 2-dimensional search. Next, we're going to be looking at a subset of the previous set of North Carolina cities, in particular just the ones that have populations of 50,000. So we can take our previous data and then do the test for, is population greater than or equal to 50,000. So when we do that, we get this set of cities returned. And if we plot those cities, first calling make map to preserve space, then actually plotting it, we get a much smaller set. And these are the major cities in North Carolina. And we're going to then plot the labels. So these are all the larger cities in North Carolina. So that's a smaller data set to work with. In terms of the number of points, the value returned is XY50. So there's a total of 16 cities with at least 50,000. We could also create data for cities with at least 125,000. Again, we start with our 84. here we can create a is vector, and that'll give us a result. But if we do that, we end up with an is vector that has 84 elements. So if we want something smaller, we could alternatively use an index vector. We do that, we get only 7 indices, and those are the cities with 125,000. That is the information from those cities, and then we can further restrict. So now we have a structure. Instead of having all those cities, we can have the cities and directly determine those that have population of 125. So we have the same 7 elements where each of those gives us the name, longitude, latitude, and population. First, let me create this information, and then I can get pretty much the same information just with this single call. And it's created that information. These are the names of those 7 cities. And then one possibility would be nice to be able to, instead of just getting one city at a time, to be able to get multiple cities at a time. What we'd like to be able to do is have a cell array with the names of the cities. So in this case, say Raleigh and Charlotte. We'd like to get the names of Raleigh and Charlotte and get the indices corresponding to those 2 cities from the set of names for all the cities. But if we do that and execute this, it's going to generate an error. And the reason is that the arguments have to be the same. So the cell arrays would have to have the same dimensions. So it can be a single string, Raleigh, and then multiple names, but it can't be 2 names and then the names of all the cities. And so that basically is a problem. One way of getting around it is we could do string compare for Raleigh and Charlotte. And then since the string compare returns logical vectors, we could use the logical OR operator. And if we did that, we'd get returned 1s in the 2 locations for Charlotte and Raleigh in the name string. The problem with that is that in terms of index, if we did it this way, and the way we've written the code, we're assuming Raleigh is the first index, Charlotte is the second index, and then the values we get returned are 2 and 6. Well, in the name array, the second element is actually Charlotte. So we've kind of lost information and wouldn't be able to actually know where Raleigh is in the string. To do it correctly, we would have to have Charlotte first and then Raleigh. We get the same 2, 6. In this case, it would work, but we'd have to essentially sort alphabetically as we call. So that's really not the most convenient way to do it. Probably a better way to do it, if this is all we had available, is to, instead of doing it in one command, just do 2 separate string compare commands in the order that we want. So first we're going to do the Raleigh call, and then semicolon. Then we're doing the Charlotte call, and we're going to take those 2 indices and call them in that known order. So now we get 6, 2, which are the indices of Raleigh and Charlotte in that order. Well, because that's such a common thing in most geocoding, essentially this is something that, I find myself struggling with all the time when I'm trying to, create data sets and doing whatever. So it was enough of an inconvenience that I looked for a way of actually making it a little more direct. And what has then been developed for MATLOG is a function called MAND, and that stands for multiple and. And essentially what this does is preserves the correct order. So using the MAND command, we can have Raleigh, Charlotte. And when we execute it, we get 6, 2. If instead we wanted Charlotte, Raleigh in that order, we'd get 2, 6. So it does what we're interested in. This is the help information for MAND, multiple and with real or stellar vector array pairs. And really it was designed really for this problem to actually make it a little bit more convenient to utilize. We can also, instead of having to type the entire name Charlotte, there's also a variation on the string compare function where you don't have to have the complete name, just enough characters to make it distinguishable. And again, since I've defined the MAND function, we can put whatever convenience in there. So basically I have the string compare option where you basically just need to have enough characters to make the single value distinguishable. So when I do that, I don't have to do all of Charlotte. I can just do CHAR and I still get the same result. But if I go all the way down to just C by itself, I get an error, and the reason is it found multiple matches. And to see what the error might be, if I look in this list, there's also Cary that starts with a C. So if I had done D for Durham, it would work, but since there's two cities that start with a C, it generated an error. So if I go to CH, then it's enough to make it distinguishable. And I could do the same with Raleigh and do lowercase RAL, and all of that's distinguishable enough that I can get the two indices that I'm intending to from this. The next example will be an illustration of allocation and how it can be done in MATLAB. We did talk about this in class. This is the more detailed example, and we're going to be utilizing the city data as our representative set of data, and we're going to use as our weights the population of the cities. So first we're going to create a 2x7 distance matrix, which represents the distance from Raleigh and Charlotte, which are the two rows of the matrix, to the 7 other cities. Notice the zeros for Raleigh in the first row and 0 for Charlotte in the second row. And then next we're going to assign the variables n and m using the size command in MATLAB. And then we're going to be calling the argmin function, and when we call it, we see that we get returned the indices of the corresponding row with the minimum distance value in it. These are our 7 city names, and then here we're going to take the population value, which is a column vector, take the transpose to convert it into a vector, and then we're going to create an allocation vector from argmin, and we're using the variable a to represent the alpha value talked about in class. And then what we're going to want to do is take the population values from the W vector and put them into corresponding row of the W matrix that we're going to be creating. So the first step is to create an empty W matrix. And we could use the zeros command, but the problem with a regular matrix like that, it is not then easy to place non-zero values in elements in a matrix. Even if we didn't really care about creating sparse matrices, it's useful to use the sparse matrix formulation. And the reason is that it allows us to specify the I and j, or row and column indices, along with the corresponding value that we want placed in that matrix. So to do that, we can first create an empty sparse matrix. Here we end up with an all zero sparse matrix that has 2x7. The nice thing is that the sparse matrix represents almost no memory on the computer. Even if it was a million by million, if it was all empty, it would have no memory space. Whereas a regular matrix, a million by million, we'd run out of system memory, even though it's all zeros being stored. As an abbreviation, we could just do this. The way we want to actually use it, though, is in this next call, where we're specifying here the ultimate maximum size of n and m. But then these 3 arguments, the first corresponds to the indices for the rows, or the I indices, you can think that way. And the second are the j indices, or column indices. And in this case, we want to assign to all of the columns 1 through m. W represents then the values that we want to place into that. And when we do that, we end up with the 7 non-zero values that are returned for the sparse matrix. We don't get all the values, we just get the non-zeros, the indices together with the actual values. A lot of times to actually see it, we'd want to use the full command, and what that does is converts W into a more traditional type matrix. And then finally, to be compatible with what we talked about in class, in this case we could then calculate the total distance. In this case, the total distance, the value of the total distance would be people miles. A more convenient way of displaying small matrices in MATLAB is to use the matlog function mDisplay, or matrix display. And if we do that, it actually then allows you to label the indices, and it also includes commas for large values. If we want then the sum of populations for Raleigh and Charlotte, if we do sum, and then by default we would sum over the first dimension. If you look at the results, you see you basically get the sum of each column, and basically it's just the overall population of that city. What we really want is to sum over the second dimension, and when you do that, you then get the total sums assigned to Raleigh and to Charlotte, or allocated to each city from the 7 other cities. which is what we intended to do. Next example is for using circuity factors to estimate what the actual road distance would be. If we have our 7 different cities, and if these correspond to the distances, I'd like to start with looking at the distance from Raleigh to Charlotte, which is 120 30 miles Great Circle distance. If I go to Google Maps, I can see that the actual road distance is 167 miles. So if I take the ratio of the two and assign it to G as a circuity factor, it's 1.28. And then since that's just a single value, what I'd like to do is to do it for several pairs of cities and then take the average of that and use that as my best estimate of what the circuity factor is for this set of data. So second example would be the city of Charlotte and Cary. The Great Circle distance is 120. Google Map distance for actual road travel is 160. Taking the ratio is 1.33. Notice here that when I called it, I assigned it to the next element of G. And since G just existed as a single scalar, by using n plus 1, I took whatever the current length of G was and added one element to the end of it, and then made the assignment to that element. That's an easy way of appending values to an array. The next example is Raleigh to Fayetteville, and that is equal to 68 miles Great Circle, 76.7 actual road. And the third value then appended to the vector of circuity estimates is 1.11. I can then reassign the mean back to G, back as a scalar, and I get the average of 1.24. So I'll use that as my estimate of what the circuity factor is for this set of points, and then I can modify my original Great Circle distances to be estimated actual road distances by just multiplying the G times the D matrix, and I get these estimates. For example, Raleigh to Winston-Salem, my estimated road distance is 114. Great Circle, it was 92.4. The actual road distance from Raleigh to Winston-Salem is 103 miles. So the ratio then is, looking at my estimate to what the actual is my estimate overestimates by about 11%. So it's probably plus or minus about 10-11% accuracy for this use of circuity factor. And the advantage of a circuity factor like this is, instead of using 3 points, if we based our estimate on probably 10 or 12 would be adequate, then with that estimate that would be reasonable, and then it could be applied to a much larger set of actual data. So that's utility, and it basically saves us from having to go and actually determine what the actual road distance estimates are. And as we do it for more and more points, we get a more and more accuracy, because the over and under estimates tend to cancel each other. The next example is using the entire set of US data, and that's just under 30,000. And to get help information, what information is available, it's more than for the North Carolina data. And in this case, it shows, in addition to the name, long lat, and population, it also has state information. And then it also has housing, land area, water area, and additional information. So we can do a similar thing and use the US city data. And then here what we're doing is using the string compare function to compare the string North Carolina with the states. And when we do that, we get a total of 739 cities. So those are all the cities, not just the original 84 cities that had populations of 10,000. These are all the cities in North Carolina. We can call make map to see where they'll be plotted, do the actual plotting. And then if we want to restrict it further and look at cities that just have the original 10,000, then we get back our original 84 sets of cities that we had in the NC City data set. So this is a way of duplicating the same information that was in the NC City data. We can use the US City data to look at more than a single city. So in this case, if we wanted to find the indices of Raleigh and Charlotte, we can use the man function, and then we can also extend to 2 additional input arguments to the man function and do the same thing for the state information. So just like we did with the cities in US City, the first example using man, We can then, this is a second example where in addition to the cities, we can also then look at states. And what MAND is doing is looking at what cities in the US city data have the same name and the same state information. And with that, we get these two indices which correspond to Raleigh and Charlotte in that larger data set. If we want to look at just Raleigh itself, then we can take the first of those indices and we get the Raleigh information. So this says that the population of Raleigh is 403,000. That's again based on 2010, so it's probably a larger value at this point in time. If we want to do more than one state, then we can basically extend similar ideas, and we can do that. And in this case, what we're going to want to do is combine both North Carolina and Virginia data. So we want to get all the cities in both of those states. One way of doing it, we could just use the bitwise logical OR of the results for North Carolina and for Virginia using the string compare function. So that would be one way of getting the information. There's 1,330. We could then do make map, and it actually is clearing enough space for both states, so I think the plotting would work in this case. So these are all the cities. This is the Washington area with the high density of cities in that area. Unfortunately, as we add more and more states to our thing, this command gets larger and larger, so it gets kind of unwieldy to work with. So as a way of making it more convenient, in MATLAB, the more command can be used to actually do this a little bit more conveniently by just putting a cell array of all of the states followed by the state information from the city data. And when we do that, I can just do that in one step. We get the same 13 and 13, 1,330 cities in both states. Here's more information about the more command. It stands for multiple OR operations. One example of its utility is, say that we wanted all of the cities that had populations of at least 10,000 that were in the continental United States. Then in one call, we can get all of the cities in the United States that have population of 10,000, which is over 3,900. And when we plot that, we see that in addition to the continental United States over here, we also have Alaska, Hawaii, and Puerto Rico. These are all the cities. You can see there's just a couple cities up in Alaska, some in Puerto Rico, and some in Hawaii. To do that all in one step, we could take the more results, which is going to be a logical vector, and then take the logical negation. So essentially this then would give us all of the cities that are not in Alaska, Hawaii, or Puerto Rico. And then at the same time, we can also check for the population being greater than 10,000. So logically, we can AND that to the OR result. And all in one step, we get a total of 3844. So when we create a new figure for those, you can see that it's, in this case, now restricted to just the continental United States. And then we can plot all of the cities in the continental United States. Continental United States is a useful data set when we're dealing with things where we expect to be able to do our transportation operations using trucking, where it's not feasible to truck anything to Hawaii or to Puerto Rico.